Thank you for joining. We are going to talk about Snowpipe streaming and Streamlit. Maybe we'll start with introductions first. So I'm Purav. I'm an engineering manager at Snowflake. My team works on data ingestion. That includes copy, Snowpipe streaming, Kafka connector. Um, and it has been, I have been working for Snowflake for about 4 years. It has been great working here and enabling all the customer scenarios. And on stage with me, I also have Brendan. He is a staff data engineer from AppFolio. Thank you for joining. So here's the agenda. So we will start with an overview for Snowpipe streaming, and then we'll transition to the AppFolio's Snowflake journey. AppFolio, we'll start with how they needed the data platform and how they onboarded to Snowflake and how their Snowflake journey has evolved over the period of time. And then we'll switch over to how they moved over to Snowpipe streaming over the last year and how that has benefited their end-to-end scenario. So let's start with the overview of Snowpipe streaming. Streaming is often a misunderstood term. Streaming is not limited to instantaneous applications, but it is a continuum. For example, say a retail company which needs an up-to-date data of its inventory every 10 minutes is a perfectly valid streaming scenario. And so is manufacturing company needing latest quality information, say at a minute's interval, is also a streaming scenario. So the graph here, the x-axis is time and the y-axis is the business value to be derived. And we believe that streaming encompasses the entire continuum and it's not limited to the summit of now. We want our customers to think through of how they can derive the peak of soon after and also the mountain of wisdom through their applications by targeting latencies that span like sub-second to several minutes to tens of minutes to even some hours. We at Snowflake, our streaming platform supports the entire continuum of applications for streaming. So this graph is a continuation of the previous slide. What this shows is the cost to business decreases exponentially as we relax the latency requirements for a given streaming application. What we want, okay, so what we have seen with traditional streaming platforms is they pigeonhole customers into thinking about applications that require sub-second latencies. And that, as this graph shows, leads to a result wherein the cost of the applications becomes too high as the data volume increases. So what we want to encourage our customers is think of the trade-off between cost and latency as you are designing your streaming applications. And we at Snowflake, our platform, provides sufficient knobs in the system so that you can reason about these trade-offs as you configure the streaming applications at Snowflake. So as we were designing the streaming platform at Snowflake, we went and talked to a bunch of our customers trying to understand their streaming scenarios. And we learned that customers are dealing with a lot of complexity. They are developing several infrastructure services and managing very complex configurations to support their end-to-end streaming scenario. Also, this process is not scalable. What we found is like building the second, third, fourth, fifth data pipeline takes equal amount of time as they were spending building the first data pipeline. Again, the cost of these applications is too high. As the data volume increases, the cost increases exponentially. And there is a lot of engineering effort required in building and maintaining these streaming applications. So we took these learnings to heart at Snowflake, and we delivered a world-class streaming platform. So streaming at Snowflake is extremely easy to use. So simplicity is a principle that we follow at Snowflake. We believe that our product should be very simple, which enables the customers to think about their business problem and not worry about the nitty-gritties of Snowflake. That's the best way to generate maximum business value using Snowflake. Again, streaming integrates well as a unified platform in Snowflake. It integrates with all the different features that Snowflake provides, like governance, sharing, replication, AI, ML, Snowpark, etc. As I talked about the trade-off between cost and latency, our streaming solution also provides knobs to control the latency. And this enables customers to reason about like lower cost if they can live with longer latency. And again, the solutions are very extensible. We have seen several connectors and application built on top of our streaming platform according to the needs of the scenarios from customers. So this was like all I talked about was in general about the streaming platform at Snowflake. Now I'm switching gears into Snowpipe streaming. So think of Snowpipe as a single tool for ingestion into Snowflake. Snowpipe supports both file-based ingestion as well as streaming ingestion. Often customers don't have control on the data source. Sometimes they are dealing with files, and sometimes they have streaming row sets. So if you have files, you can continue to use the traditional Snowpipe for file-based ingestion. And if you have row sets, you can use Snowpipe streaming to stream these row sets continuously into Snowflake using Snowpipe streaming. Both of these solutions scale very effectively. We have seen millions of files and terabytes of data ingested per hour per account using Snowpipe. And Snowpipe streaming also scales very well. It is effective both for trickle case of kilobytes per second ingested, as well as like tens of GBs of data ingested through Snowpipe streaming. So now about Snowpipe streaming. These are the salient features for Snowpipe streaming. With Snowpipe streaming, now customers can directly stream their data into Snowflake tables. We support exactly once and per channel ordering in Snowpipe streaming. We have the native Snowflake Kafka connector, which is natively built on top of Snowpipe streaming, and it supports exactly once ingestion. Snowpipe streaming is very low latency. In production, we see large throughputs being supported with an end-to-end latency of 5 seconds to query time. And then, as I said, like very high throughput is also supported. We have seen 10 plus GBs per second being ingested with Snowpipe streaming. There is very low overhead. Again, this is the simplicity philosophy I was talking about. There is minimal configuration and setup needed for setting up your Snowpipe streaming. It is very low cost, both for the flood and the trickle case. And it integrates really well and provides a framework on top of which we have built several connectors, including the native Kafka connector, database connectors, including the Postgres and the MySQL database connectors, which are in public preview now, and then the AWS Kinesis connector. So we GA'd Snowpipe streaming a year ago, and we have been continuously improving Snowpipe streaming, and we have also been listening to all the feedback from all of you customers and improving Snowpipe streaming. The adoption has been really great. It is exponentially growing month over month. So this slide lists some of the improvements we have done over the last year. So we added the max client lag parameter on the client side. This enables customers to reason the trade-off between cost and latency. We have also improved greatly our file migration story. So now there are updates on the client side, improvements so that we generate better sized partitions on the server. Also, our file migration runs much faster and scales to much more data throughputs. And we have added a lot of changes which reduces the cost of file migration. And this cost are already being passed on to the customer. We added OAuth authentication support. There is more error handling support. We added support for drop channel and reset offset token. Schema evolution was like a very heavily requested feature. Now Snowflake Kafka connector natively supports schema evolution. It got GA'd like 2 or 3 months ago, and it's used by a large number of our customers. Here are some of the key learnings of running Snowpipe streaming in production over the last year. It's an extremely easy transition for customers who are using Snowflake Kafka connector. It's only a configuration change. We support a very wide range of scenarios. We have seen kilobytes of data ingested per second to tens of GBs of data ingested per second. We have seen customers with 1 to thousands of Kafka topics, and each topic with like 1 to thousands of partitions. All these are seamlessly supported really well with Snowpipe streaming in production. Several Snowflake and partner connectors are built on top of Snowpipe. I touched on this on the last slide. So another thing is our engineering team is busy building the next generation of Snowpipe streaming. And here we are building a lightweight REST API using which you can stream row sets using this REST API into Snowflake. This will require very lightweight client SDKs compared to like a heavyweight Java SDK today. And we envision lightweight applications like mobile devices as well as like IoT sensors stream their data directly into Snowpipe streaming into the Snowflake streaming platform. Another key learning is customers are seeing vastly reduced latency and cost using Snowpipe streaming. We have AppFolio on stage with us, who adopted Snowpipe streaming, and they saw some of these benefits over the last year. So at this point, we can transition to the AppFolio story, and I'll hand over the mic to Brendan.
Cool. Okay, thanks, Purav. So good afternoon, everyone. My name is Brandon Stanley, and I'm a staff data engineer at AppFolio. And I'll be providing you all with an overview of our data platform and its architecture. But before I dive into the platform and its architecture, I'd like to give you a little bit of context around what it is that we do at AppFolio. So AppFolio is a technology company that streamlines and automates real estate management. And our mission is to build a platform where the real estate industry comes to do business. Our platform is built on scalable infrastructure and is meant to serve as the system of intelligence, engagement, and ultimately the system of record. AppFolio's platform provides various features and offerings to enhance the user experience, including Stack and Realm. Through Stack, we enhance the value of our PropTech ecosystem. Through Realm, our generative AI and LLM capability, we provide a workflow orchestration engine that helps automate our customers' business, where customers can literally ask, tell, and teach the product to do something. In addition to being able to apply common services like payments and insurance horizontally. Our platform also powers industry segments. Industry segments are the target audiences that are used in how we define real estate at AppFolio. For us, this includes investors, property managers, owners, residents, and vendors. We've been in the market for over 18 years, and our company has grown to over 1,500 employees. We serve over 20,000 customers with over 8 million units managed on our platform. Through our journey over the past 18 years, our platform and product offerings have grown, and so have our data sources. From our sharded MySQL databases hosting our operational data, Salesforce systems, and marketing databases, it became apparent that there was a lot of useful information and insights contained within these data sets, which led us to ask the question, can we harness the insights contained across our disparate data sources to help grow our business? To think about this across different scopes at AppFolio, let's take a look at the questions that were being asked. Within product analytics, what features deliver the most value to help inform our product development teams? Can we build dashboards to track KPIs such as revenues, ARPU by segment, or ARPU of a new customer versus a tenured customer? From an insights perspective, can we determine what our market share across different geographic markets is? Within the AI and ML space, can we use our data to power performant AI and ML models? And from a risk and fraud analytics perspective, we wanted to know, how do we detect an anomalous behavior on our platform? Since we run a large payments business, it's imperative for us to monitor transactions and trends closely to help safeguard our customers and our business. It became obvious that we needed a centralized data platform, and we decided to adopt Snowflake as our data cloud provider. The left of this diagram is really just the tip of the iceberg in terms of what data sources we surface through Snowflake, but for the purposes of this session, I'll be focusing on the subset of data sources for which we leverage Snowpipe streaming. So let's travel back to 2019 when we started our journey with Snowflake. At the time, our focus was to mirror our operational data across our sharded MySQL databases, which back AppFolio's property manager software. To do this, we built a nightly ETL pipeline written in Ruby and orchestrated using Airflow. We issued select statements to every table to extract the data from MySQL and load it into S3. We then copied this data from S3 into Snowflake. With any batch system, there's always an element of latency. The ingestion latency, which refers to the latency between our source systems and Snowflake, was 24 hours. At the time, we didn't have logical data zones that you would typically find in data warehouses or data lakes, like a raw zone or a standardized zone. As a result, our end-to-end latency, or the latency between our source system and the layer in Snowflake through which the data was surfaced, was also 24 hours. This pipeline proved to be useful to us. However, there were some challenges. The first challenge was data freshness. The pipeline ran nightly, therefore the data could be stale by up to about 24 hours. This led us to ask the question, how can we increase the frequency at which the data was updated for consumption? The second challenge was the increased database load. Every night when the ETL job would run, we would issue select statements, select star statements to every table against every database. For our larger tables, you can imagine how inefficient of an operation this was. In addition, we weren't incrementally loading our data to capture the deltas between the last time we ran the ETL job. So what this means is every night we were reloading these tables. This led us to ask a second question. How can we avoid putting a load on the source databases? So in 2021, we decided to re-architect our pipelines and adopt a streaming-first approach. To incrementally capture our source database information without putting a load on the underlying databases, we use Debezium as our CDC tool to load the data into Kafka. For those of you who are unfamiliar with Debezium, it is a change data capture or CDC tool meant to replicate and to capture and replicate data from your databases by reading its logs. We then use the Snowflake Sync connector, which was also running on Kafka Connect, to load the data from Kafka into our Snowflake raw zone. We created streams on top of these raw tables to capture the incremental inserts, and then merge the data within these streams into our standardized tables on an hourly cadence. As part of this re-architecture, we adopted an ELT approach and also added logical data zones that I mentioned, like our raw zone, which contained the atomic change events in their original format, as well as our standardized zone, which contained the upserted mirror tables with the CDC, using the CDC data from our raw zone. The standardized zone is the zone that was made available to our end users. As a result, we were able to reduce our ingestion latency, which is the latency between our source systems and the raw zone, from 24 hours or a day to 1 hour, and our end-to-end latency, which is the latency between our source systems and our standardized layer, from 24 hours to 2 hours. This slide provides a little bit more insight into the merge SQL or statements that are executed hourly in Airflow. As I previously mentioned, we have created streams for each of our raw tables. We then select from these streams and merge into our standardized zone on an hourly cadence. Using the logic that we see here, we account for inserts, updates, and deletes by looking at the operation of each CDC record. This ELT pattern worked really well for us, and we decided to expand this solution to 2 other data sources, including our clickstream data and our custom server-side event data generated across our AppFolio applications. So in 2022, we implemented solutions for extracting and loading both our clickstream and server-side event data. For our clickstream data, we use Snowplow to capture and replicate clickstream events from our AppFolio applications into Kafka. And similarly, for our custom server-side event data, we built custom Kafka producers using the SDKs available in Ruby, Java, and Python to send server-side event data into Kafka. One of the highlights about this solution is how extensible it was. Because we were using Kafka and the Snowflake Sync connector, adding a new data source into Snowflake was as simple as producing data to a topic in Kafka. Because the Snowflake Sync connector was configured to copy any data from topics in Kafka into our Snowflake raw zone based on a naming convention via a regular expression, all we really had to do was produce the data into those topics. In addition, we dynamically updated our Airflow DAGs to account for any new tables. Here, we're just highlighting the merge and insert SQL that we're using for our clickstream data. So as I previously mentioned, for our CDC data, we're merging our data from our Snowflake streams into our standardized tables on an hourly cadence, accounting for inserts, updates, and deletes. However, for our clickstream and server-side event data, these are strictly insert only because the concept of updating or deleting a clickstream or server-side event didn't apply to us. So whatever data shows up in the stream would get inserted into the standardized table on an hourly cadence. So this pattern proved to be scalable, extensible, and useful to AppFolio, but we knew that there was still room for improvement, specifically around the latency. While it was great to drop our ingestion latency from 24 hours to 1 hour in our raw zone, and from 24 hours to 2 hours in our standardized zone, we knew that there were still some use cases that would benefit from a further reduction in latency, which led us to ask the question, can we ingest the data even faster? We saw the slide that Purav spoke to earlier about streaming not necessarily being tied to instantaneous data applications. However, there are certain use cases that require low latency. The key takeaway from this chart is that for time-sensitive use cases, the value derived from your data diminishes over time. This graph is not meant to be a generalization and only applies to time-sensitive use cases. At AppFolio, one of the use cases that benefit from a reduction in latency is within product analytics. Reducing the feedback loop between feature deployment and customer engagement helps us be more nimble and react more quickly to customer feedback. Another time-sensitive use case lies within insights. Being able to analyze and act upon information more quickly leads to more informed and accurate decision-making. And having fresh, up-to-date data is fundamental to this. Within risk and fraud analytics, detecting, triaging, and resolving anomalous behavior by analyzing the most current information available increases our alertness and our agility. So one of the most obvious questions we asked at the time is, why not just reduce the buffer flush time? And there are two reasons for this. The first, and before I dive into the two reasons, the buffer flush time is the Snowflake Sync Connector configuration that controls your data ingestion rate into Snowflake. And so there are two challenges with this. The first is cost. Snowpipe loads data into an intermediate cloud storage layer prior to loading the data into the corresponding Snowflake table. So in the long run, the resulting file ingestion and cloud storage costs would result in our platform becoming too costly to maintain in the long run. The second reason is that there is an inherent lower bound on the latency that's achievable due to this intermediate storage cloud layer. There's a limit at which you can load your data into Snowflake before running into limitations within the system itself. But thanks to the constant innovation and push forward by Snowflake, we were able to adopt Snowflake streaming, which reduced our latency without having to increase our costs. Last year, we seamlessly updated our Snowflake Sync Connector configurations and changed the Snowflake ingestion method from Snowpipe to Snowpipe streaming, and also changed our buffer flush time from 1 hour to 10 seconds, which reduced our ingestion latency from 1 hour to 10 seconds, and our end-to-end latency from 2 hours to 1 hour. Even though we reduced the latency of this entire system, we did not increase our costs due to the efficiencies unlocked by Snowpipe streaming that were mentioned earlier. Here again, we just want to highlight the differences between this merge SQL and the insert SQL for our clickstream and CDC data. So again, for our CDC data, we're merging our data hourly, accounting for inserts, updates, and deletes. And for our clickstream data, we're strictly inserting the data. One of the questions that you may be asking is, why didn't we further reduce our end-to-end latency to take advantage of the 10-second ingestion rate into our raw zone? And there are two reasons for this. The first is merging or inserting the data more frequently would result in higher warehouse costs. And the second reason is a similar lower bound problem. So due to the sheer size of some of our CDC tables, it takes a couple minutes to actually merge the data because of the total amount of volume in those tables. As a result, merging the data might actually take longer than the frequency that we would actually want to achieve. But we were still able to unlock the benefits from loading the data every 10 seconds into our raw zone using Snowpipe streaming. This table summarizes the latency between our raw and standardized zones, as well as the DML types that's used to load the data from the raw zone into our standardized zone. As we saw, for our raw zone, the latency was reduced to 10 seconds across all of our data sources. The end-to-end latency for our CDC data in the standardized zone is 1 hour because of the cost and performance considerations that I mentioned. But for our clickstream data and event stream data, server-side event stream data, we were able to leverage what we refer to as near real-time views, which allows users to access the data as soon as it lands in the raw zone, even though we're inserting into our standardized zone on an hourly basis. So let's talk about these near real-time views and the ability to achieve an end-to-end latency of 10 seconds with these near real-time views. If we take a look at, so from the past, we know that if we look at our raw zone, we're loading data from Kafka every 10 seconds using Snowpipe streaming. Let's assume that there are 2 records and a third was just inserted, denoted in the green text. We have a Snowflake stream that captures the incremental inserts into our raw table. We can see the record that was just inserted sitting in the stream. And then we have our standardized table, which inserts data from which contains data that's inserted from our stream on an hourly cadence. And the key thing to note is that the third record that was just inserted into our raw table has not yet made its way into the standardized zone. But if we look at this near real-time view definition over to the right, it is selecting from both the standardized table and the stream via a union. Therefore, when a user actually queries the view, we can see the third record that was just inserted into our raw table, even though it hasn't been inserted into the standardized table yet. This view is what we make available to our end users and how we are able to present the data in near real time without having to insert into our standardized table more frequently. You might have heard about AppFolio Streamlit applications at last year's summit. This slide shows a complete picture of how we use these near real-time views with Streamlit for fraud investigation and product experimentation tracking. On the left, we have our various data sources being loaded into Kafka, which then flow into Snowflake via Snowpipe streaming. We have our streams capturing the incremental additions to each of the raw tables, which are then loaded into our standardized tables via Airflow. We then have our near real-time views, which perform a union between the standardized tables and the streams, which are made available to the end users directly or via the Streamlit applications. This is a more comprehensive architecture diagram of AppFolio's data platform and shows how we serve the various use cases that I mentioned at the start of the session, from dashboarding to risk and fraud analytics. In our serving layer, we use many tools to transform and present the data, including Airflow, Streamlit, dbt, Tableau, Hex, Mixpanel, Mode, Redash, and much more. Snowpipe streaming has proven to be extremely beneficial to us at AppFolio. To illustrate the scale at which we are using Snowpipe streaming, we are capturing data from over 40 million tables across our 20,000 customer databases. All the change data capture events from our MySQL databases, in addition to our clickstream data and our custom server-side event data, have amounted to over 600 billion records being ingested through our pipelines. These records are consolidated into over 2,800 Kafka topics corresponding to a common MySQL table, clickstream event, or a server-side event type. We have over 200 Kafka Connect tasks that use over 10,000 Snowflake channels, each of which correspond to a Kafka partition, which are then used to load the data into over 2,800 Snowflake tables. To summarize, we began our journey on Snowflake with a series of custom batch jobs executed nightly, resulting in an ingestion latency of 1 day. We then switched to a streaming-first approach, using Kafka, Kafka Connect, and Snowpipe, reducing our ingestion latency to 1 hour, and providing us with the ability to easily scale. We were then able to reduce our latency even further due to the adoption of Snowpipe streaming, which resulted in second-level ingestion without increasing our costs. Modernizing our platform impacted us on multiple fronts, but here are a few worth calling out. In product analytics, we reduced the feedback loop between feature deployment and engagement from customers, making us more nimble. We strengthened the insights derived from our data, empowering users to analyze and act upon information more quickly via real-time analytics and Streamlit. And we improved our risk and fraud analytics capabilities by being able to detect, triage, and resolve anomalous behavior by analyzing the most current information available. With that, I'd like to thank you all for your time.